let's look at multiplexers and demultiplexers. All right, so in a digital system, we might have a whole lot of data stored in different places, and we need to do a lot of different things with that data. So an inefficient way of getting something from point A to point B would entail having, a direct connection for everything that goes on through there. So let's say that there's a wire connecting for every bit of data, and it goes everywhere that it could ever want to go. So what multiplexing does is it lets us take a lot of data or a lot of information and choose what gets on a transport. Okay, so we could take 8 things and choose which of these 8 things we're going to put on a bus, and then we could use a demultiplexer later and choose where those things go. And the best analogy I could think of is, I live in Jasper, my mama lives in Philadelphia. There's not a road that goes directly from my house to her house. I have to get on a road, then I get on another road with other people, then I get on another road with other people. And we're all using the same roads, and they just kind of branch out, and we multiplex ourselves a little bit. Like, so the highway, you could think of as a big copper wire, and depending on when we get on there, we've got a little space. So if I called my mama, they would put a little bit of data of my voice on the line, and then they would multiplex it with a little bit of data from somebody else and somebody else. And then whenever it gets to my mama, they'll demultiplex it and just take the data that I put on the line, and somebody else's mama that they're calling from somewhere else would be demultiplexed data for them calling to tell her they love her. So we don't have millions and billions. Well, we got billions of wires, but we don't have a direct wire from me to my mama, and then from me to my wife, and then me to my other family, or to me and my friends. And there's not a direct line radiating from everybody. We're all sharing the same bus, and then demultiplexing lets us take that information and sort it out to where it needs to go. Okay, so the best analogy, I think, would be a telephone, or little side streets feeding onto a big highway, and then little side streets coming off. Okay, so you can only have one car at one spot at one time on that highway, but we can share it. And that's what we're doing here. Instead of having, billions of roads connecting everything directly, we multiplex information onto one line, and then we demultiplex it off to where it needs to go. Okay? So the easiest way to kind of get an intuitive look at this is, let's look at the humble AND gate. Okay, so we know that the only time we get a 1 out of here is if both of the inputs are 1. Okay, or all of the inputs are 1. So if I put a 0 here, we know that a 0 ANDed with anything is equal to a 0, right? Because we cannot get a 1 out of an AND gate if there's a 0 on any of the inputs. Okay. Now, if we had a 1 here, then whatever is coming in the other way is going to come out the output. Okay, so if we have a 0 here, this is always going to be 0. If we have a 1 here, it's going to be whatever this is. If it's a 0, AND gate won't let it through, so we get a 0 out here. If it's a 1, we got a 1 and a 1, it lets it through. Okay? So let's make a simple 2-to-1 multiplexer. Okay? So we've got this gate. And got this gate. Now, if it's 2 inputs, when we put a 1 here, whatever's on these is going to come out of here, right? So we could think of this as an enable. All right, so going back to our encoders and decoders, okay? So I could use one wire to decide, like, if I want to enable things going through those gates. So if I put a 0 there, it's always going to be a 0 on the output. It doesn't matter what's coming in on here, okay? All right, so we're going to do multiplexers and demultiplexers. I want you to understand that we can use an AND gate as a gate. You know, that this wire right here, you know, we could tie it to a switch. And if we flip that switch, then the data that comes in, that side is going to go out. If we don't push that switch, it doesn't matter what data is coming in. It's always going to be off. Okay? All right, so it's easier to look at a demultiplexer first. So let's build one. So what a demultiplexer does is it takes one input and some address lines. And then depending on what those address lines are, so if we have 2 address lines, we can have 4 outputs, okay? If we have 3, we can have 8. If we have 4 address lines, we can have 16, okay? So if I put a 0, 0, 0 on this DMUX, so we'll call them DMUX, then whatever data is coming in here is going to be coming out of this output. If we put in like 0, 0, 1, whatever data is coming in here is going to be coming out of the first output, or, you know, second output, output 1. So output 0, output 1. Okay, so how could we do this? Well, let's do a very simple one. So we're going to have data coming in here. And then right here, we've got a 1-bit address. All right, 1 bit gives us 2 possibilities. It could be a 0 or it could be a 1. Give me just a second. Hey, babe, is everything okay? Yeah, I'm in the middle of a video. It's like 20 minutes long and I don't want to waste it, so I'm talking on it. Can I call you right back? I love you. Bye, y'all. I guess it was only 10 minutes, but all right. So if we put a 0 on this address line, this top gate is not going to open, right? Because it doesn't matter what the other input on the AND gate does. If we have a 0, it's going to be a 0. So this one up here, if we put address 0, nothing's coming out of this side. But we've got an inverter, so the address 0 is going to turn on this gate, and whatever data we put in here is going to go out here. Okay? So we've got a 1 to 2 Demux. Alright, that should kind of make sense. Like, we have data going to both sides of this, but the address is going to dictate which gate actually lets things through. Okay? So let's make this a little bit harder. Let's do a 2 address. Alright, or a 2-bit. So 2 bits, we've got 4 addresses. Okay, and we're doing the demultiplexer right now. Alright, so we've got an AND gate, and we need the data and we need the address information. So if we've got a 2-bit address and that's 2 bits of data, so we need 3 bits to make this work. Okay, so let's make it work when 00 is called. Okay, so we're going to have 2 address lines, and they're both going to have a 0 on them. So right there, let's call this address 0, address 1. Okay, so if those are both 00, then this gate is active, and it's going to take whatever is on that data line. Cool? Alright. The data is going to be the same coming in. Like we're taking one wire and then we're splitting them off into many different places. And we'll say this is A0 and this is A1. Alright, so let's do 0, 1. Alright, so A1 or A0 is a 0. So we need to invert it to get that to turn on. But A1 is going to go straight through. Okay? So when 0, 1 is on the address lines, now all the A0s will be tied together, all the A1s will be tied together. I just don't want to draw a bunch of crisscross lines that will, get it harder to read. Okay? So that should show you that whatever's on the data is going to come out when we've got a 0, 1. Okay, what about a 1, 0? The data is going to be the same, but then A1 is already a 1. I mean, A0 is already a 1, so we don't have to invert it, but now A1 is a 0. So we're going to have to invert that. Now when we have 1, 0, the data is going to come out here. Okay? And then a 1, 1. So we've got the data coming in. They're all sharing the same data. It's a 1, 2 something. And then depending on how we set up these address circuits, only one gate will be active at a time. Well, A0 is already 1. We don't need to invert it. A1 is already a 1. We don't need to invert it. So that is a demultiplexer. And they'd look like this, where you'd have data coming in, so you'd have a data line, you'd have an address, another address, however many bits you needed for that. So a 2-bit would have 4 outputs. Okay, and depending on what the address is, we would be able to steer that data to different places. Alright, so I did a demultiplexer first because a multiplexer is just like a demultiplexer, but it's taking a lot of data and putting it onto one line. Okay, so let's think about how that would work. Okay, so now let's say we've got data 0 and we've got data 1 and we've got data 2 and we've got data 3. And we want to make a circuit so that when we put an address on a line, that data goes out of there onto that one line. So we can choose who's going through that multiplexer. Okay? All right. We're going to do the same situation here, but instead of having the data lines tied together, the data lines are not tied together because we have different data coming in. We'll still have our address, so 0, 0, we need 2 inverters because both of those are going to be 0. We want to turn that on. All right, if this one's 0, 1, this one doesn't need that, but a 1 does. So all of those gates are going to kind of work the same way as they did before, but instead of all the data lines being tied together, we're going to tie all the output lines together. Okay? And I hope you understand why this works. All right, so if we ORed all this, right, and we made sure that only one of these gates is active at a time. Let's put the A1 back up there. Then, so let's say I put, 0, 1 on my address. I know that the only data that's going to be going through that OR gate will be D1. Okay? So the OR gate is going to collate all that information, and as long as my addressing is correct, then I know that the stuff that's coming out of the OR gate is only coming from the gate that I had right there. So if we put a 0, 1, so that turns that on, or that lets that start passing. If it's 0, it's going to be 0 right here. If it's 1, it's going to be 1 right here. And that output is going to be following whatever we put on that address. Okay? So we're going to try to do deeds. So pull up deeds, and we're going to try to do both of them this time. I'm trying my best to get it in a decent time frame, but I really want to get both of these done this week because this is super powerful and where things start getting really interesting. Okay, so let's make that multiplexer. Okay, and so we're going to make a 2-bit multiplexer. So let's take 3 input AND gates and let's put them like that. Okay. All right. Now, I could put knots on all of these that needed knots. Or I could do something like this. If I know, 2 bits isn't going to be that big of an issue. Okay? But if I know that once I get past 2 bits, I'm going to have a whole lot of things that are A and A naught, B and B naught, C and C naught, D and D naught, etc. Sometimes it's a lot better to go ahead and get a representation of both of those. Okay? So I'm going to take an input dip switch and let's do let's just take 2 input switches. Okay? And let's go ahead and just make let's say that this is address address 0. And then we're going to put this one, which will be address 1. Okay. Now let's make our life easier. Let's put the least significant bit over here. Okay. Cool. So that when we flip these, we'll have 0, 0. Then we can flip this for 0, 1. And then we can flip this for 1, 0. All right, let's scoot this just a little bit. What we're going to do is we're going to give us a A0 and an A0 not, an A1 and an A1 not. Okay, so I'm going to take an inverter, and instead of putting an inverter on every gate, that's kind of wasteful. All right, and I want you to start kind of recognizing that. So I'm going to make a connection here, and this is going to represent A1. I'm going to make a connection here. This is going to represent A0, and then escape. This side will represent A1 not, and this one would represent A0 not. All right. So let's go ahead and move these just a little bit. All right. Now, this gate we'll say would be 0, 0. So if that's 0, 0, then we need to take the not from each one of these. All right, we'll say a not will go on the highest input. So we'll put A1 not right there, and we'll put A0 not right there. Okay. All right. Now we need 0, 1. So this one would be already a 1. So we'll grab it from the not inverted aspect there. But this one will be A1 not. Right? So that one would be a 0. We need to invert it. So we're going to go get that one. Okay. Let me scoot down just a little bit. All right. 1, 0. So we need A1 to be not inverted. So we'll go ahead and put that right there. But we do need to invert A0 because it's 1, 0. And so that's going to be a 0. So we're going to have to invert it so that one will come on. Okay? And then 1, 1. So all we got to do is come off of this one. This will be a 1, so we don't have to invert it. And this one will be a 1, so we don't have to invert that. Now, that's one way of simplifying circuits. That's one thing we can do to simplify circuits. When I did that multiplexer, drawing it out, for 0, 0, I already had 2 inverters up on here. And then when I had 0, 1, I had an inverter on here. 1, 0, I had an inverter here. So I just saved 2 inverters by recognizing that I could just tie those inputs together because if I need an A not or A1 not, I've already got it. Like I've already had it before. Okay. So we've got a 4-input multiplexer. Let's go up here and get our data. So now let's take the input dip switch and let's take a 4-bit. Okay, and we're going to put it right here. And we're going to call this data. We're going to take Control W gives you a wire. We're going to take each separate switch and tie them onto each one of our inputs. Alright, so we want to check that this is working. So let's take some of those test LEDs. Let's put them in front of each one of these. And we're just going to do this so that we don't get too confused. Because if we build the rest of the circuit before we verify that this works, and this winds up not working, we won't know what's working and what's not. Like, it's a lot harder to troubleshoot when we've got 50 million things, when you can troubleshoot as you go. So we're going to simulate this, say yes, and we're going to call this Mutz Demux. Okay, so go ahead and put your last name underscore MUX underscore DMUX. All right, now we've got address 00. So let's see if we can get, yeah, all right, so that gate's working, right? All right, like none of the rest of the gates are going to work. All right, let's go to 01. So the next one, we'll start putting data out. Okay. But none of the rest of them will work. Let's go to 10. Oops. Was that the one I just did? Let's go to 11. Alright. Now that one's working. Okay. Now, the reason I got us to do this right now is because the demultiplexer and the multiplexer look a whole lot alike, right? So, all we have to do now to make this a multiplexer is put an OR gate on it. So we can take all those lines and get them onto one wire. But the only thing different about this and the demultiplexer is the fact that we've got all of those data inputs has been separate instead of tied together, right? So go ahead and stop this. Before we go farther, what I want to do is I want to take this, okay, and do a control copy, and then do a control V, and then we're going to move this over here, okay, then escape. Alright, so the only thing different about this and a demultiplexer is all those data lines are, separated. The only thing different about this and a demultiplexer, everything that's different about this and a multiplexer is what I just said. Everything that's different about this, the only thing is these aren't OR gated yet. Okay, so let's go ahead and let's take an OR gate. So we've got 4 different outputs. Let's put an OR gate there. Okay. And then we're going to control W, get a wire. We're going to go off of here. All right, so that's the, that's the end of our multiplexer. So we're going to have whatever data we put on the address line out here, okay? And the only thing we have to do over here is tie all these wires together. So this is now our data input. All right, so what we should be able to do is put data on the line based off of these addresses and then choose where those go over here. So let's go up and simulate. Go ahead and save it. Okay, so if both of my addresses are 0, 0, I'm going to take data from the first address and I'm going to move it, and it's going to go across one line and get over here. Okay, so if I turn it on, I get data out over in this address. If I go and if I change this, so we've got 0, 1, then that data is going to get on the line, and then this is the destination address. So I'm taking some data from the second memory location and I'm putting it in the first, right? Let's say that I wanted to put it in the third. I could put 1, 0 for 2, 0, 1, 2. And now, as I change this, I'm still only messing with address 0, 1 of the source, but I'm sending data out 1, 0 over here. Let's go change this to 1, 1. So I want the data that's in address 0, 1. Oops. And I want to put it out at another storage location at address 1, 1. Okay. So I've got one wire. I can take all this data, move it through that one wire, and then put it wherever I want to go. Okay. So let's say that I want to take some from this address 1, 1 and I want to put it in the destination address of 1, 0 or 0, 0. So as this data goes, this LED up here will go. Okay, so yeah, that was 30 minutes, but we got a good amount done. Okay, I want you to think on this. I want you to, really contemplate the power that we've got. Okay, because we would have to have, imagine if we had 8 bits of this and we need to get it over here. We'd just start having just a huge problem. We can use multiplexers and demultiplexers to get a lot of information back and forth. Okay? So when you build it, you can use it. Like once you prove that you can build a demultiplexer and a multiplexer, we can take stuff like this. All right, so let's say a multiplexer 2 to 1. Like, this is just like that little 1 bit. We've got a selector bit, and it's going to take one of these inputs and put it out that queue. But what they did is they abstracted it. They took all that circuitry and made it so that you didn't have to think about it. Now we've got a box that represents all of that circuitry. The circuitry you just did right now, once you prove that you can build it, you can start using it. So we'll take a 4 to 1. So we've got a 4 to 1. We've got 2 address bits, 4 inputs, and 1 output. That's what this is. Once we build it, we can abstract it so we don't have to think about it too hard. We just say, okay, whatever data is on this address is going to come out this output. You can also now that you've done a demultiplexer, you can do a 1 to 4. Okay? So that's an abstraction of what we just built. But now you can see the power, right? And for next week, since you've already built a decoder, y'all can start using an abstraction of an encoder and a decoder. Where is it? All it's got is a priority encoder. But we can start using those, and since we already know how they work, we're okay with using those abstractions, right? I didn't want you to start using these decoders, encoders, multiplexers, and demultiplexers without knowing what was actually going on, because you see a box and you're like, there's no ands, ors, and nots on that box. But inside there are, okay? Everything that we use is built off of those primary components. All right, I hope it wasn't too bad. I'll probably make up for it with the bookwork. But y'all have a good one. Looking forward to seeing you. Let me know if you got any problems.